Okay, so welcome back to the second part of my lectures for the Les Houches School. So in the previous talk, I talked to you about tunneling and electric field control of magnetism. So today we will touch upon related but different notions. And the main topic will be spin charge interconversion using two-dimensional electron gases based on strontium titanates. So again, I want to thank the people who contributed to this work. This is the people in my lab and the postdocs and students who work on this topic. And I want also to thank very warmly my colleagues in SpinTech in Grenoble, in particular Jean-Philippe Attanet and Laurent Villa. Also, we had collaboration with Marc and the student Pierre at the LPS, and with Ingrid Mertig and our group in Halle. So in the previous lecture, I talked to you about spin polarized currents, spin polarization, which is determining the amplitude of the TMR in magnetic tunnel junctions. And here I want to explain to you what we mean by spin currents, and in particular pure spin current. So you have here four examples, four different notions, and I want to take you through that slowly. So the first case is the most simple. You have two electrons with a spin up moving to the right and two electrons with spin down moving to the right as well. So you have in total four electrons moving to the right. So you have a charge current corresponding to these four electrons, and you have zero spin current because you have the same amount of spin up and spin down moving in the same direction. So this is an unpolarized current, no spin polarization. Here, this is what we discussed in the last lecture, spin polarized current. So here you have, for instance, two electrons with spin up going to the right, one with spin down going to the right. So you have three charges. The charge current is shown here. But in addition, here you have a finite spin current that corresponds to the imbalance of spin up electrons, if you wish, moving to the right. When you have only spins, only electrons of only one spin direction that are moving together in the same direction, this is a fully spin polarized current, okay? And here you have a large charge current and a large spin current as well. And finally, there is a last situation where you have that corresponds to two electrons with spin up moving to the right and two electrons with spin down moving to the left. So here you have no charge current, there's no net flow of charge, but there is a finite and large pure spin current because you see that you have a motion of the spin angular momentum to the right in this case, okay? And this is a large pure spin current. So coming back to the junctions and vertical spin transport, another way to put what I was showing, explaining in the previous lecture in vertical spin transport is that when you have two ferromagnets sandwiching an insulator, for instance, in alternate junctions, you see that we were discussing in terms of spin polarized currents, but the spin polarized current is the superposition of a charge current and a pure spin current. So here you can also picture this by assuming you have the flow in parallel of a finite charge current and finite spin current. In the in-plane geometry, you can also work in this in-plane geometry, and this has a number of advantages. Things can be a little bit different. So here you have one channel, and then which is typically can be a nanotube, 3,5 2D electron gas, or a graphene layer, or something like that. And here you're going to deposit transverse contacts, transverse ferromagnetic contacts. And here you are going to apply a current, to run a current between the end of the channel and one of the ferromagnets. So here you are going to inject the charge current and also a spin current, but the spin current will also diffuse sideways in the channel. And here you will only have pure spin currents, okay? No, no net charge current flowing. And this has a number of advantages in terms of detection of the signal because you avoid artifacts due to charge currents. And then you can detect the amplitude of the spin currents reaching the ferromagnet here. The advantage of the in-plane spin transport geometry is that you can apply a gate, for instance, and you can manipulate the transport of the spins in the channel between one electrode and the other electrode.